Hello, everyone. I'm Dr. Townsend. I just wanted to start off this class by giving a little overview of the course and a review of some important distance measurements that we will need throughout this class. So first, I want to talk a little bit about what astronomy actually is. So really, it's just the study of objects beyond Earth and the processes by which these objects interact with each other. It's kind of the textbook definition, but it's also humanity's attempt to kind of put us and the world as we know it in the context of the larger universe. And this is based primarily on interpreting light and looking for patterns. And we see evidence that humans have been doing this throughout the world. Stonehenge on your screen here is a prehistoric structure from the UK that was likely used to mark the summer and winter solstice. Then we have, Angkor Wat it's a Hindu turned Buddhist temple in Cambodia, and it was designed to mark the spring and fall equinoxes, right? The sun on these days rises just in line with the central tower. So we see evidence of this from civilizations all over the world at all times. Mapping the stars and looking for repeatable patterns, though, wasn't just for fun. There were really practical applications as well. So it was used extensively for navigation. So an astrolabe, what this man is holding here, is a device for measuring precise angles of the sun and stars from the horizon. So this told ships what their latitude was. So it helped them navigate oceans. Um, Agriculture, we can talk a little more about this later, but in most places on Earth, the sky changes from month to month. Some stars are only visible in the winter and some in the summer, etc. So knowing when certain stars start to appear, it's kind of like a rudimentary calendar to let ancient people know when to plant and when to harvest. And also the astronomy and the sky were important for culture. So the stories ancient people attached to stars, they transmitted their culture and law from generation to generation. So on the screen here is actually a picture from the southern hemisphere of the great emu, which is used by indigenous people in Australia and the surrounding islands. How this is oriented in the sky would help people really determine what time of year it is. So this is just um, there were a lot of ways that knowing and understanding the sky and how it appeared to change over time was important. For thousands of years, humans looked to the sky with just their eyes, but that changed in the early 1600s, about 1609. Galileo invented the telescope, and that really revolutionized astronomy. So, for example, on this side of the screen here, kind of illustrations of what Galileo saw when he first observed Jupiter's moons. And this observation put in serious doubt the geocentric model of the universe. So, this idea that everything in the universe and the sky revolved around the Earth. This was one of the first pieces of evidence that really said that that is not true. We've come a long way though since Galileo's telescope in our technology. So we have telescopes in space. Like these are a couple of the most famous ones. We have the Hubble Space Telescope right here and the James Webb Space Telescope here. They're just examples, but there are many others that view many different other wavelengths of light. There are also these so-called next generation telescopes that we're building on Earth. So these ground-based telescopes like the Vera Rubin Observatory here in Chile, which will survey the entire sky in only a few days. It's named for astronomer Vera Rubin, who uncovered important evidence of dark matter. So usually astronomy is all about interpreting light, but we've really expanded our capacity to send rovers to other planets to test samples directly. So here's kind of a family portrait of several of the Mars rovers with two humans for scale. Um, this is one of one of the more famous ways that we have sent rovers to other planets, but we've sent rovers to the moon as well. Then there is this ongoing revolution in so-called multi-messenger astronomy with the use of gravitational waves and neutrinos. So neutrinos are these tiny, tiny subatomic particles that we think are produced in supernova. So being able to detect those tells us a lot about the solar system, or I mean the galaxy. Interpreting astronomical observations is basically looking for what changes occur over days, months, and years. And these observations help place us and the Earth in context. So, for example, how the moon, sun, and planets move throughout the night gives us clues about our relationship to other objects in the solar system. We can also think about how near and far other stars are to our solar system and what near and far even mean in an astronomical context. So once we understand this, we can start thinking about other galaxies and how far away those must be. And we can think about how galaxies fit into the big picture of the universe as a whole. So distance in astronomy can get a little overwhelming. So I wanted to do just a little example. So this might be a typical road sign you might see on the side of the highway around Albany, except maybe for the distance to to the moon, right? We might talk about how New York City is a little over 2 hours away, or Buffalo is maybe 4.5 or 5 hours away. The moon, though, clearly is much, much further than that. So, how long would it actually take to drive to the moon if we could, to drive that 240,000 miles? Well, let's say we drove 60 miles an hour the entire way. So that's a straightforward calculation. We just divide 240,000 miles by 60 miles per hour, and we get 4,000 hours. So it would take us 4,000 hours to drive to the moon. This, though, that's still kind of hard for me to wrap my head around. So let's say that we were really booking it and we decided to drive 20 hours a day. So if we divided 4,000 by 20, we would get 200 days. It would take us 200 days to drive our car at 60 miles an hour from Earth to the moon. If we want to think about that in terms of months, we've got about a little over 6.5 months, almost 7 months really, to drive 60 miles an hour from the Earth to the moon. And that's really like our closest neighbor, right? And it still takes that much time. So distances really only get bigger from here. So when we talk about, we're talking about distances on Earth and like the size of the Earth, we're really talking about kilometers or miles. Like that would be the appropriate unit to use. So the radius of the Earth is about 6,400 kilometers. Its circumference is about 40,000 kilometers. And the Earth-Moon distance in kilometers is about 384,000 kilometers. This is kind of the scale at which we normally operate, right? Um, we usually don't even get as far as the hundreds of thousands of kilometers, but this is something that is kind of understandable in our normal everyday life. That starts to change as we want to talk about the solar system. So the Earth-Sun distance is about 150 million kilometers or 93 million miles. And we have defined this distance to be one astronomical unit or one AU. This makes talking about distances in the solar system a little bit easier. Like if we just define the average distance between the Earth and the Sun to be one astronomical unit, then we can define everything else in the solar system in relation to that. So, for example, Mercury, the closest planet to the Sun, it is only zero point 0.4 AU. So it is less than half the distance from the Sun that Earth is. Venus is almost as far out, right? It's about zero point 0.7 AU. Mars is 1.5. Then we start to get really far, right? Jupiter is 5 AU, Saturn 9.5. Uranus, kind of way out in the outer solar system, is 19 AU, so 19 times as far from the sun as Earth is. Neptune, 30 AU. And then we have these structures in the outer solar system, the Kuiper Belt, which is where Pluto kind of hangs out. It's 40 times as far from the sun as Earth is. And then there's this region called the Oort cloud, where we believe a bunch of comets kind of come from. Um, this is where we're talking extremely long distances here, 50,000 AU, 50,000 times as far from the sun as Earth is. But even this really isn't enough when we're talking about kind of the rest of the galaxy or even the universe. Um, because stars, whether they're quote unquote nearby or not, are actually really quite far away. So usually these types of distances to nearby stars are measured in something called a parsec. So this is a portmanteau of the two terms parallax and arcsecond. So parsec is it's based off a measuring method called stellar parallax. And basically what that does is it uses the apparent movement of foreground object to estimate distance. So if we're here on Earth trying to measure this star, we would measure its movement relative to the background. You can kind of see how that might work in this diagram here. But a parsec is the distance from the sun to an astronomical object that has a parallax angle of 1 arcsecond. So we have this very defined measurement for what a parsec is. An arcsecond, by the way, is an angular measurement on the sky equal to 1/3600th of a degree. So it's a really small angle. A parsec, though, to put it in context, is about 3.1 times 10 to the 13th kilometer, which is a lot of kilometers, probably too many to be really useful. Or we can talk about it as 3.26 light years. So remember, light years is the distance that light will travel in a year. And in a lot of ways, it's easier to think about things in light years than parsecs, right? The closest star to the sun is Proxima Centauri, and it's about 4 light years away. So if you sent a message to that star, that means that it would take our message 4 years to get there if it was traveling at the speed of light. And if they responded right away, it would take 4 years to come back. So basically, it would take about 8 years to confirm dinner plans over text with someone from Proxima Centauri. But so those are the units we would use to describe things like nearby stars that are actually much further away than things either on Earth or in the rest of the solar system. But even that is starts to get a little bit squishy as we talk about galaxies and beyond that. The Milky Way is the galaxy that we live in. We're not able to yet get a picture of the galaxy because we can't leave it, but this image here is a pretty good idea of what our galaxy looks like. And in our galaxy, light years is a really good way to measure distance, right? So the diameter of the Milky Way is about 10,000 light years. the thickness. So it's kind of, it has a thickness right here. You can see it from the side, an illustration. It's about 1,000 light years thick. And the distance from the center of our galaxy to our solar system, to the sun, is about 30,000 light years. So remember this, so it takes light 30,000 years to travel this distance. It takes about 10,000 light years for it to travel all the way across the galaxy. So even this though is a little bit hard when we think about very, very long distances, like distances in between galaxies. We start to get cosmological distances. And when this starts to happen, astronomers will use something called redshift, or more generally, Doppler shift. So you've likely experienced Doppler shift before with sound. If you've ever uh, been, standing around and heard an ambulance coming your way, you likely heard the pitch of the siren get higher as the ambulance speeds towards you and then get lower as it speeds away. So this is the Doppler shift as it applies to sound. The wavelength of sound coming from a moving source, it changes. In astronomy, we use the Doppler shift of light to determine distance. So if we look out into the universe, we notice that the universe is expanding and other galaxies are moving away from us. As a result, the wavelength of light coming to us appears to change. If we know what speed the universe is expanding at, and and if it's expanding at a nearly constant rate, then the speed is going to be proportional to the distance. And the redshift of light can be used as a distance scale. So redshift is much easier to work with at these distances than describing galaxies as, trillions of miles away. So there are a few kind of major questions in astronomy, and one of those is, what can the solar system and the stuff inside it tell us about its own history? So we have models of how the solar system formed, but they're pretty incomplete. The solar system, we think, is about 4.5 billion years old, and a lot has changed in that time. So what can our observations about the solar system today tell us about its evolution over time? So for example, we actually know very little about Venus right here. Venus is the hottest planet in the solar system with an atmosphere that is toxic to us, but we really don't have any idea if it's always been like that or if it's something that happened to the planet, something that kickstarted a runaway greenhouse effect. There are several missions in the works that will launch in the next decade to try to figure this out. The outer solar system is also a little bit of a mystery. So these are images of Pluto that came in 2015 from the New Horizons spacecraft. And they show really two types of ice interacting here on the surface of that dwarf planet. And so we've never seen this before. This is kind of new information about Pluto. So even though our solar system is by far the closest thing we have to study, we still have an awful lot to learn. Another question in astronomy has to do with our sun and what the sun can tell us about other stars. So the sun, we will talk about, I think next week, maybe the week after, is a star. It's one of billions of stars in the galaxy, and one that we can really kind of study in the most detail. So if we can figure out really how the sun works, like what's going on in its interior, then we can compare it to other stars and it can give us some insight into how stars change over time, right? How stars are born, how they live their lives, and how they ultimately die, sometimes in a big supernova explosion and sometimes not. So this right here is an image of the sun really at different wavelengths taken simultaneously. So studying how these features vary tells us something about what's inside the sun. Another major question is what we can actually learn about the emergence of life in the universe and whether there's life anywhere else. This question is on the top of a lot of people's minds. And as our technology gets better, and as we can start detecting more exoplanets, right, or planets around other stars, it's natural to ask whether or not there is life out there and whether it's similar to our own. So looking for evidence of life on exoplanets may be a ways off, but last year NASA launched the Europa Clipper, which is a satellite heading toward Jupiter's moon Europa, and it is designed to figure out if life could exist under that moon's icy shell. And if we find something, what does that tell us about the origins of life on our planet? So this is really a hot topic and ongoing question in science. Okay, so that was just a quick overview of the course. I just wanted to put a slide summarizing these distance scales on your screen at the end. In astronomy, we deal with these humongous distances, and getting used to really how we talk about those distances will be important in this class. That is it for now, though. You're free to move on to the discussion question and our first look at the moon.